Buenas tardes. That's my only Spanish. It's my great pleasure to be here today. Thank you so much for having me. I thank the Global Roundtable for Sustainable Beef. I thank Silver Team. I thank all of you for having me here today. It's a distinct pleasure for me to be back. It has been almost 30 years that I have been to Paraguay. In fact, to the Chaco. I spent some quality time in the Chaco with Dr. Glatzle close to 30 years ago, and many months, and I enjoyed the warm climate and the insects and the rattlesnakes and everything that you have to offer to a young student. Since then, I did my master's degree, my PhD degree in Texas, and then I went to California where I've lived for the last 20 years. I'm a professor and air quality specialist in the Animal Science Department at UC Davis, and I study the impact animal agriculture has on air quality, on all different kinds of gases that livestock produce, including greenhouse gases. And little did I know that this topic would one day become as hot and as heated as this one has become. When I first dealt with methane, I just dealt with methane because it's an energy loss. We don't want to lose methane because it's a net energy loss to our production. That's why we cared about methane 20, 30, 50 years ago. But today, we also care about methane because it's a greenhouse gas believed to have a contribution to the warming that has become a major international issue. So I will now spend about 40-something minutes with you on the topic of livestock and greenhouse gases, and I will focus particularly on methane, because methane is a central greenhouse gas in this whole discussion. In my opinion, methane is the Achilles heel of animal agriculture today, because all of those people who don't like you so much, I call them my special friends, these people who don't like animal agriculture have honed in on this topic of methane because they view this as the greatest vulnerability of animal agriculture. So, I will get started by pointing out some very brief comments that are not deeply scientific, but that help explain what greenhouse gases are believed to do to our climate. So what you see on this slide here is the sun radiating down solar beams to the surface of the Earth. Normally that radiation would be reflected back into space if there weren't these so-called greenhouse gases, gases such as CO2, methane, nitrous oxide, and these gases pretty much form a blanket over our atmosphere, retaining some of that solar heat back in our atmosphere. And without greenhouse gases, life on Earth would not be possible. It would likely be too cold. We need greenhouse gases. The problem is, or at least that's what climatologists tell us, the problem they say we have is that we are putting too many of these greenhouse gases out, therefore this blanket is getting too thick. So I'm not a climatologist, I'm an air quality specialist, so I'll talk to you about this particular gas methane and what I know about how it's produced and why it's special and why it's very important for us to know about the difference. When it comes to greenhouse gases, such as those three, CO2, methane, and nitrous oxide, they are most often compared to one another using a so-called matrix called the global warming potential, GWP100. Please remember that abbreviation. GWP100 says that methane is roughly 28 times more potent in trapping heat from the sun as CO2 is. And that is why so many people feel we need to concentrate on methane because it's a potent greenhouse gas. Nitrous oxide, according to this, is even more potent, 265 times more. So if, let's say, a ranch produces 10 tons of methane, and you want to know how that relates to CO2, then all you need to do is multiply the 10 tons of methane from your ranch times this factor, 28. And then you arrive at a number of 280 tons of CO2e, CO2 equivalent. So what this GWP 100 pretty much says is that methane is CO2 on steroids, just a much more potent CO2 type greenhouse gas. But That, as you will see, does not capture the true nature of that gas. Methane is different from the other greenhouse gases insofar that CO2 and nitrous oxide are not really destroyed in the atmosphere at a short time period, but methane is. This slide here shows what's very important and oftentimes overlooked, the so-called global methane budget. You see here on the left side of this budget different sources of methane, such as fossil fuel production and use, agriculture and waste, biomass burning, wetlands, and so forth. These different sources of methane produce a total of 558, let's call it 560 teragrams of methane globally. These are all the sources. This is how much methane is produced. And this is where normally the discussion around methane ends, because people are only interested in what produces that gas. But it's very important to understand methane is not just produced, methane is also destroyed. On the right side of this budget, you see that there are sinks that amount to 548 teragrams. In other words, 558 are produced, 548 are destroyed, and that leaves the balance, which is highlighted here in red. Still a number we seek to reduce, but certainly one that's grossly different than just focusing on the one side of the budget. If you now look closer to this budget, you see a large arrow pointing down. This one. And this is now very important. This large arrow pointing down underneath says, sink from chemical reactions in the atmosphere. What does that mean? Imagine this fist being a methane molecule. Within approximately a decade or so, this methane molecule meets another molecule in the air that's called a radical. To be precise, it's called a hydroxyl radical. And when these two meet, the methane and the radical kills the methane. It destroys the methane. And that on average takes about a decade to happen. So remember, hydroxyl radicals are in the air, they're always in the air, and when they meet a methane molecule, they kill it. The same does not happen for other greenhouse gases, but it does for methane. And that is why it's so important to know about the fact that it's not just produced, but also destroyed. You will see in a minute how profoundly that impacts the difference between these gases. So the take-home message on this slide is methane is not just produced, it's also destroyed almost at equal rates. And that means if you have a constant source of methane, then that constant source produces methane, but an almost equal amount is being destroyed by these hydroxyl radicals. I repeat that. A constant source of methane produces methane, of course, but an equal amount to what's produced is also destroyed from constant sources. What I just described, the hydroxyl oxidation, this destruction of methane, leads to this gas having a short lifespan of approximately a decade. And that's in sharp contrast to the other greenhouse gases, which are not short-lived but long-lived. CO2 has a lifespan of 1,000 years. Nitrous oxide has a long lifespan as well, of over 100 years. But methane is pretty much gone after a decade. All right? Now you will see why that matters so much. But before I do that, I will talk to you now about the so-called biogenic carbon cycle, or where the carbon that's in the methane, the CH4, where the C in the CH4 comes from and where it's going. So what you see here is the biogenic carbon cycle. Where does the carbon come from? The carbon comes from atmospheric CO2. During photosynthesis, atmospheric CO2 is taken on by plants that our animals eat. Photosynthesis, of course, also requires sunlight and water, but the carbon comes from the atmosphere. It's then converted, that carbon is then converted into carbohydrates, such as cellulose and starch. Cellulose is the world's most abundant biomass. And sooner or later, let's say a ruminant like a cow comes along and eats the above ground vegetation. And with it, the carbohydrates. Some of those carbohydrates in the rumen then are converted into methane, and some of that methane is belched out. A process called enteric fermentation leads to enteric emissions. Methane is belched out. Some more methane is produced from the animal manure. But my question to you is this carbon in the methane, is that carbon new and additional carbon added to the atmosphere? No, it's not. It's recycled carbon because it was in the atmosphere before. Before it went into the plants, it was in the atmosphere before. It has changed forms from CO2 to methane. And while methane is in the air, it's more potent as a greenhouse gas. It's more heat trapping in the atmosphere. But after approximately 1 decade, that methane is destroyed. The process is called hydroxyl oxidation. These are the radicals destroying it. And this is an atmospheric removal of this gas. Again, a constant source of methane does not add to additional warming. A constant source of methane causes constant warming, no additional warming. Why do I stress this point, additional warming, so much? Because the Paris Climate Accord and other agreements don't have an emissions goal, they have a temperature goal. And the temperature goal is not to add any additional warming beyond 2 degrees centigrade. That's the Paris Climate Accord. We don't want any additional warming caused by any particular sector, and that includes the cattle sector. So how do we get to a point where we don't cause additional warming is the question. So, but before I go there, where does that CO2 go through? It goes into the atmospheric pool of CO2 from which plants, for example, then take on some carbon for photosynthesis again. So this is a short-lived cycle here. This cycle takes a little over a decade. Now, is this cycle around livestock methane similar or different from greenhouse gases produced from other sources? The number one source being fossil fuels, that means transportation, power production, cement industry. Is this cycle different from fossil fuel-derived greenhouse gases? Now I take you to that process, which I think is significantly different, because the fossil fuel carbon, the oil, coal, and gas, is former vegetation and animals such as dinosaurs that died, decayed, fossilized over hundreds of millions of years and accumulated underground. And then humans took those fossil fuels out of the ground. Approximately half of the fossil fuels have been extracted over the last 70 years. We take that carbon out of the ground and we do what to it? We burn it. So where's the carbon now? It's in the atmosphere. Every time we burn fossil fuel, we take carbon that is ancient and that was underground, and we put it into the atmosphere. And that, ladies and gentlemen, is a one-way street from the ground up into the air. Again, on the livestock side, the biogenic carbon cycle is one where you have atmospheric CO2, it goes into the plants during photosynthesis. Some of the carbon stays above ground, but the majority goes below ground into the roots, and from there, through soil microbes, into the soil, a process referred to as soil carbon sequestration. Very important to countries like Paraguay, Argentina, Brazil, and so on, where you have a lot of grazing land. So a lot of the carbon that humans have put into the atmosphere eventually makes it back into soils, and if we treat the soils well, if we don't disrupt them too much, that carbon can stay in the ground. So then our vaca here comes along and eats some of the above ground vegetation, belches out some methane, but that methane then becomes CO2 again. So you have a relatively short-lived cycle on the right side, and you have a one-way street of carbon on the left side. The greenhouse gases generated by livestock versus those from fossil fuel sources contribute to different amounts of carbon added to the atmosphere. Most climate scientists will tell you that the main source of greenhouse gases stems from the use of fossil fuels, oil, coal, and gas. But those people who don't like you very much will say, no, it's the cat. We have to reduce methane from ruminants. And I already told you a little bit of the difference between CO2 and methane, and I will tell you a little bit more about it to show why it's so important to get the narrative around methane right. So first of all, so I think everybody here knows soils and forages are very important to help us first take carbon out of the air and then trap it in the soil. Soil carbon sequestration. If you wonder how different ecosystems compare to one another with respect to carbon, here is one slide showing it. You see up here different land use types, and down here you see different carbon storage types. You can see that, yes, forests do trap a lot of carbon, but so do grasslands. Look at that here, that's temperate grasslands. We have many grazing lands that store as much or more carbon than forest lands. It's not true that it's only forests and forest-type ecosystems that help us trap carbon. A properly managed rangeland can store a lot of carbon. And we, through adaptive management, can help to maximize the amount of carbon stored in the soil. Now, colleagues of mine from Oxford University, who don't really know anything about cows, but who know everything about greenhouse gases and how they act from a physical perspective, years ago said the way we are quantifying methane currently, using this GWP 100, is wrong. Because methane is not simply a more powerful CO2. Methane is different. Methane has an atmospheric removal associated with it. So they said, we need to get the methane narrative right. We need to develop a new matrix to quantify the impact of methane on warming. They said years ago that this unit that has been used for the last 30 years, called GWP 100, that this unit GWP 100, if you use that for a constant source, such as constant cattle herds, that this unit overestimates the impact of that constant methane source on warming by a factor of 4. I repeat that. If you have a constant cattle herd, they produce a constant amount of methane. If you use GWP 100 to characterize how that constant herd affects warming, then you are overblowing the impacts by a factor of 4. I've been saying that for years. Some people listened, but many people didn't. They thought this is just creative accounting. They thought this is just greenwashing. Those colleagues from Oxford didn't believe it was greenwashing. They said this is accurate. Because GWP 100 does not account for the atmospheric removal of methane. Now, they developed a new matrix called GWP star, and GWP star does account not just for the production, but also for the destruction of this gas. And it characterizes the actual warming impact of methane. So that has since been published dozens of times, GWP star, and is promoted as an alternative matrix for complex sources such as livestock. If you wonder whether or not anybody believes this, that this old unit here overblows the impact of constant sources on warming by a factor of 4, yes, people do believe it now. Last year in August, I thought I couldn't believe my eyes when I read the Intergovernmental Panel for Climate Change, IPCC, report called AR6, and the AR6 report said, and I quote, by expressing methane emissions as CO2 equivalent emissions using GWP 100 overstates the effect of constant methane emissions on global surface temperatures by a factor of 3 to 4. The most authoritative climate body in the world said the unit we've been using for the last 30 years overblows the impact of methane on warming by a factor of 3 to 4. I hope everybody gets why this is such a big deal. Because we have constant methane sources in countries like this, in countries like your neighboring countries, in most livestock areas in the world, except for some developing countries where herd sizes are increasing. So GWP star is believed to be an alternative to GWP 100, one that does a better job characterizing the impact of methane on warming. Before I talk about that in detail, I want to explain to you the difference between two important gases. The one is CO2, the other one is methane, and how they respectively warm the planet. CO2, imagine you were to live 20 miles away from work. You drive on Monday to work. When you do so, you put CO2 into the atmosphere. Remember, CO2 has a lifespan of 1,000 years, so it stays there for pretty much ever. On Tuesday, you drive again, you burn gas, you put new and additional CO2 into the atmosphere, in addition now to the stuff from Monday. On Wednesday, you drive again, on Thursday, and so on. Every time you burn fossil fuel, you add new and additional CO2 to the atmosphere, adding to the previous day, the previous week, the previous month, the previous year, the previous decade, all the stuff your parents and grandparents and so on put into the atmosphere. That's carbon that is adding up in the atmosphere. That is increasing, leading to increasing concentrations of CO2. That's what CO2 does. Currently, methane is treated as if it were to accumulate just like CO2 does. And that means currently methane is treated as a stock gas like CO2, accumulating in the atmosphere. But I already told you, methane does not accumulate because methane is both produced and destroyed. Methane, ladies and gentlemen, is not a stock gas. Methane is a flow gas. It's both produced and destroyed. And that's why it looks like this. If you have an estancia, and you've had this for 40 years, and your cattle numbers are the same, then the amount of methane your animals have produced and the amount of methane that had been destroyed are roughly in balance. No additional warming as a result. But every time you burn fossil fuel, you add new additional carbon to the atmosphere. So the one is a stock gas, the other one is a flow gas. I now give you an analogy, and I use two bathtubs for it. The first bathtub analogy is one for CO2 and how CO2 warms the planet. Imagine a bathtub where you have a faucet, but you do not have a drain. Whether you turn the faucet on low, on medium, or high, you're always adding additional water to the bathtub. The levels rise. Can the levels go down? No, there's no drain. Okay? They can never really go down by a lot. The CO2 side of things goes up, 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 and up. And every time it goes up, it causes additional warming. The methane bathtub is different because that one has a faucet and it has a drain. And the drain is always open. The drain stands for the hydroxyl oxidation, this atmospheric removal process. If you turn the faucet on low, or let's turn the faucet on normal first. Normal water into the bathtub means you put water in, but an equal amount comes out through the drain. As a result, the water level remains stable. It doesn't go up or down. Because you put water in, but you take the same amount out. If you turn the faucet down on low, but your drain is open, what happens to your water level? I see fingers going down. Exactly. The water level goes down. The same is true for methane. If you reduce methane, you reduce warming. Only if you crank that water faucet up all the way. Then you put more water into the bathtub, then you let go off through the drain. And then then the levels go up. And going back to the methane and what that does to warming, if you increase methane over time, you increase the related warming. But that's a short-term effect, but that is a real effect. So remember, the one is a stock gas, the other one is a flow gas. They are not the same. And now I show you how that pencils out when you do the math. I will show you three scenarios here. The first is this scenario. By the way, this comes from those colleagues in Oxford. The professor's name is Miles Allen. He's one of the IPCC chairperson. So they predicted three scenarios. One where methane over 30 years on the x-axis increases by 35%. The second one is where methane in another scenario is pretty stable. Maybe we slightly reduce it by 10%. And the third one is a scenario where methane is strongly reduced by 35%. A strong reduction of methane over 30 years. How would these three scenarios, the increasing, the stable, and the decreasing scenario of methane, how would they be depicted if we were to use the old unit GWP 100? that has been used throughout the world up until today, GWP 100. GWP 100 would say that in all three scenarios, the increasing, the stable, and the decreasing scenarios, we would add a lot of additional CO2 equivalent emissions to our atmosphere, causing a lot of new additional warming. But we know that's not true because it doesn't consider the atmospheric removal of this gas. Now I show you what GWP star does, the new unit. GWP star only agrees with GWP 100 in the first scenario. If we add a lot additional methane to the atmosphere, it causes a lot of additional warming. That's the blue north of the x-axis, new additional warming. But if we have a slight reduction of methane over 30 years, then you don't see any blue of the north of the x-axis. You actually see a little bit blue south of the x-axis, and a negative sign in front of the number. What does that mean? That means we are not causing any new additional warming. We are not causing any new additional warming if we hold stable or even slightly reduced methane. And in the bottom scenario, you see what gets me most exciting. And that is that if you reduce methane by a lot, you're pulling a lot of carbon from the atmosphere. And these climatologists who predict this kind of thing, they will tell you that this is causing significant negative warming. That's what they call it. And negative warming is a fancy word for cooling. If you reduce a lot of methane, they believe, then you are pulling carbon from the atmosphere, much as if you were to plant trees or forages that also take carbon from the atmosphere during photosynthesis. Okay, so a reduction of methane leads to a reduction of warming. If we were to be able to, let's say, do this here, a strong reduction of methane from a dairy industry in a given locality like California, or the beef industry in Argentina or so, if that reduction were 30, 35, 40%, then the negative warming from that methane reduction would be so good that it would offset other emissions, such as nitrous oxide, CO2, offsetting them and leading these industries to a point of climate neutrality. And this is really a sea change. You will never get to a prediction of climate neutrality by using GWP 100. It's not possible. But you will achieve that vision if you look at it in a matrix that's fit for purpose, and that is GWP star. What I just told you does not mean that livestock globally is off the hook. In fact, livestock globally is increasing in its methane. And the reason for that is that in many developing countries, herd sizes are growing because the demand for animal source food is increasing. And because of that, globally, methane is going up, and that's why all this focus on methane will not just subside. In many regions, though, methane is going down. In many regions, methane is going down from livestock. But globally, at this point, it's not. For example, in the United States, we used to have 140 million beef cattle back in 1970. Today, we have much fewer beef cattle, 90 million. So we have 50 million fewer beef cattle, but we are producing the same amount of beef today as we used to with a much larger herd. Here you see slaughter numbers in the United States over time. They have been going down, but the production of beef has been going up. Today the US produces about 18%, 18% of global beef, with 6% of the global beef herd. That development has reduced the environmental footprint of beef in that locality. If we were to achieve a situation where for the beef in orange and the dairy herd in blue, the greenhouse gases, particularly the methane, goes down drastically by 30, 40% over the foreseeable future, then we will reach a point by which we achieve climate neutrality. And that is the point where we don't cause any additional warming. No more additional warming. The negative warming caused by methane reduction will counteract the positive warming on nitrous oxide, CO2. leading those industries to a point of climate neutrality. And that is a point, ladies and gentlemen, where industries sell carbon credits off to other industries, like the fossil fuel industry. We now in California have a situation where Shell, BP, BMW, Ford, and so on buy carbon credits from farmers. Because these are credits they can't generate themselves. We can generate that. Because when we reduce methane, we can get these credits. We now in California have a working carbon market. A market that more and more farmers partake in and actually benefit from. So we will not get to climate neutrality by just doing business as usual. We do have to reduce methane in particular, and we can reduce it through different means. Performance of cattle, better efficiencies, better reproductive rates, better forages. There are certain feed additives to reduce enteric methane. There are certain ways as to how to manage manure and so forth. All of that can help us to achieve this point. Now you might ask, is it possible, Frank, to get to a point where we get to this here, where we get to this, a strong reduction of warming? Is that possible that we get there in the livestock sector? In California, we have a new law that mandates a 40% reduction of methane, 40% reduction of methane to be achieved by the year 2030. At first, our farmers thought that is never achievable. We can never reduce 40% methane. The legislature, however, had something, actually for the first time ever, they did something good. I shouldn't say that, don't quote me on that. But they did something good, which was to say, we want our farmers to reduce methane, but we know they can't do it alone. So instead of using the cane approach of saying we deploy rules and regulations and fines, they used the carrot approach of saying, if you are willing to reduce methane, we will help you financially to get techniques and technologies going to reduce that gas. The state of California took about $1 billion at hand, 1 billion with a B. And farmers bought technology to reduce methane gas, particularly from waste storage. And now I'm talking about dairies, okay? We have a very strong dairy industry in California. 20% of the US milk is produced in California. And so our farmers now covered their lagoons where the manure is stored. So they covered the lagoons, and you see it here. This is a typical California dairy with 1,500 cows. This is what used to be an open storage lagoon for the manure. Now it's no longer open, it's now covered. And this covered lagoon is now trapping the so-called biogas that's generated underneath. And you see that biogas bulging out here. This biogas is 60% methane, 60% methane. And methane is high in energy. You can burn methane directly and make power from it. Or, and that's what we do in California, you take the biogas and you convert it into a fuel type for vehicles. It's called renewable natural gas. If you take dairy biogas and you make it into renewable natural gas fuel for vehicles, then the state of California considers that the most carbon negative fuel type there is. And that means that's a good thing, okay? And as a result, the state of California pays you, the farmer who does this, the so-called low carbon fuel standard credits. It's a long word. Low carbon fuel standard credits. These credits are very high. So let's assume the average dairy makes $4,000 a year for the sales of their milk. If they do what I just said, they sell their biogas, they will get another additional $2,000 per cow per year for the sale of their biogas and the conversion into fuel. $4,000 for the milk, $2,000 for this. We have many dairies that have done what I just showed you, and it's not cheap. This technology is not cheap, but many dairies have done it. After about 2 years, they break even for the cost, recoup the cost. What it looks like is this. This is a dairy biogas fueling station, okay? So the dairy renewable natural gas is now going to those semi-trucks, replacing diesel, and because several dozen dairies have done what I just showed you, we already today have a 25% reduction, or a 30% reduction of methane achieved at this point. And we just started this 3 years ago. So our goal is 40%. We are already today at 30%. And all we have done was cover some of the lagoons. In addition to this, we at the university are working on feed additives, things you can add to the diet of cattle that can reduce enteric methane, the methane that comes out of the front end. We have looked at things such as these additives here. And as you can see, some of them have a pretty astounding mitigation effect. We have found that feed additives can reduce anything from 10 to 50% of enteric methane. But I want to caution you, some of the more effective feed additives have some unintended consequences. Some of those feed additives can have toxicological effects, where the active ingredient is a well-known carcinogen. In the case of seaweed, the world is talking about seaweed, and I'm slowing everybody down saying, let's wait a minute, okay? Let's wait a minute. Yes, it's effective in reducing methane, but it produces compounds that are not healthy for people to consume. So we first need to figure out how to get all of this produced in a way that is cost effective, that is efficient, that's not dangerous to animals or, of course, people. But in the next 5 years, we will have things in the feed store. And today, as of today, we have large international companies like Nestle, Starbucks, large chocolate producers who pay the feed additives for the farmers that supply them with milk or meat entirely. These big companies are now driving this. It's not governments, it's companies like McDonald's, Burger King, Starbucks, Nestle, and so on. They're driving this. So for those of you in the room who say, you know, I don't like this whole discussion about climate change, I don't think livestock has anything to do with that, that is your prerogative to feel that way. But the people who buy your products are totally focused on this issue. And they have goals to reduce these emissions. And they will not go back. So I can only tell you what I have learned is we have to understand greenhouse gases such as methane. We have to understand that methane is only a problem if we don't manage it. Methane can be a solution if we do manage it. Because if we reduce methane, then we can reduce warming. And we can tell people, not just have we set goals for the future to reduce our carbon footprint, but once we achieve that, we help society in achieving their climate goals. And that way you become a player. If you go the other way, like this way, I don't believe in any of that, you will not get anywhere with those people who are your customers. That is what I've experienced over the years. Okay? And we can argue over this for hours, but that is what I have experienced over the years. So there are several ways as to how you can affect emissions. It's not just feed additives or manure. It is to improve the reproductive rate. That's a big deal here in South America, where reproductive rates are still below what they could be. Improve the health sector. In many parts of the world, veterinary care is not really provided very well. The genetics has a huge potential for improvements for both the feed crops our animals eat, but also the animals themselves. And the feeding of more energy-dense diets in many cases also helps to reduce, for example, methane. All of that helps us to relatively shrink herd sizes in many of the regions where herds were huge, now they're much smaller. For example, in the United States, we used to have 25 million dairy cows. Today we have 9. We went from 25 to 9, but with the 9 today we are producing 60% more milk than we used to with a much larger herd. It has reduced our carbon footprint by 2/3 for a glass of milk. So that is possible in other places as well. So with that, I still have 5 minutes. I will briefly talk about something that I think is a big deal. This slide here shows global human population. And it's called the 2050 challenge. What you see on this slide here is a very steep growing curve here. I'm a little over 50. When I was a little boy, we were right here at 3 billion people. When I was a little boy, there were 3 billion people in the world. Today, there are 7.8 billion people in the world. And by the time I'm an old man, there will be 9.5 billion people in the world, meaning throughout my lifetime, human population on this planet will have tripled. 3 times more people on this planet during our lifetime. But we don't have 3 times more natural resources to feed all these people. And that means we have to become really good at how we produce food and very efficient in how we produce food. And we need to use the land that we have at our disposal as efficiently as we can. And you have just seen some examples in the Chaco during your trip. Land that had previously not been used for food production is now being used for food production. And I think that a lot of that land use is really important. So this is called the 2050 challenge. If we take a look at world from space, you see this circle over Southeast Asia. There are more people who live inside the circle than outside the circle. A huge market for countries like yours. Huge market for countries like yours. And it continues to grow. Asia will continue to grow by about 40%. Africa will grow almost half. The Americas are relatively stable and Europe will slightly shrink with respect to human population. But while all of that happens, the total amount of resources we have to feed all these people is not really changing in any major way. So, this here is the distribution of cropland throughout the world. What you see here in color is the land that we have available to grow crops in the world. And now I want to show you one simple trick that I think is very powerful. I've used it many times. What you see here is a regular sheet of paper. Imagine this sheet of paper being the surface of the entire earth as you see it here. I now take this sheet of paper and I fold it in half. And then I fold it one more time so that I folded it twice in total. And now it's roughly the size of a postcard. What you see now is the total amount of land in the world. The difference between the large sheet and this is water and ice. This is all land. Is everybody with me? This here is my business card. And the equivalent amount of land in the world represented by my business card is all agricultural land. The difference between all land and all agricultural land are jungles and deserts and cities. That's all agricultural land. Now I take my business card and I fold it into one piece that's 2/3 and the other piece that's 1/3, and then I rip my own business card into pieces. So again, this is all agricultural land in the world. The larger of the two pieces, the 2/3 piece, is the agricultural land that we call marginal agricultural land. It's called marginal because we can't grow crops there. Why not? It's too hilly, or it's too rocky, or it's too dry, or it's not fertile enough. We cannot grow crops there. Ladies and gentlemen, what do we do with this land today? We graze it with ruminants. Why do we do that? Because that's the only food-producing land use we can use this land for. Because the only thing that grows there is largely cellulose, the world's most abundant biomass, and the only animals that consume that and make human food from it are ruminant livestock. When those anti-livestock people say we use all that land in the world to produce livestock, they're not lying. But what they're not saying is that if we wouldn't use it for livestock, we wouldn't use it at all for food production. We could make some golf courses out of that, or build cities here, but we could not grow crops here. And that leaves me with the last third of my business card, which is the arable agricultural land. This is marginal agricultural land, and this is arable agricultural land. This land, ladies and gentlemen, can be used to grow crops. That is how limited we are in the world to grow food for the 2050 challenge. And I urge you to use this kind of communication with people in cities and so on, because they oftentimes don't understand. They just don't understand why we put cattle on land, why we graze animals. They don't understand how daunting the challenges are if we don't. So with that, I come to a close. I think we have a few more minutes for questions and answers. And I thank you very much for your attention.